Alrighty, so here we are, motion on a curve. So now a curve on a road is simply a portion of a circle, right? So it can be considered a type of uniform circular motion. Now, what kind of people need to know this kind of stuff? Civil engineers, okay? Civil engineers. I have a friend who's a big-time civil engineer, and I was talking to him about this actually one day, and he says, oh, I got a document just the other day that you might want to have a look at. So he emailed it to me. It's like really thick. I think I still have a copy of it somewhere. And it basically shows, they just all use charts about how, what the curvature of roads have to be and what the banking has to be and all this kind of stuff. So, but this is the physics sort of behind it. So the net force on a car traveling around a curve is the centripetal force. Of course, that's mv squared over r, and it's directed toward the center of the curve. Now, for a level curve, there's two types of curves. There's level ones, and there's banked ones. Where would you find a level curve?
Streets, turning.
Yeah, just on a regular street, right? Like, or even like the little sort of curves where they, you know,
Roundabouts.
well, not so much a roundabout. I'm thinking, you know, out by KFC there, where you come off that corner.
Oh,
They're like a little turning it lane kind of thing. So that type of thing, a level curve. The centripetal force will be supplied by the friction force between the tires and the roadway. So generally, lower speeds. A bank curve can supply the centripetal force by the normal force and the weight without relying on friction. So they bank the curve when you're talking about a higher speed. If you think about auto racing, NASCAR, whatnot, they bank that curve, okay, so that they can travel faster. If they didn't bank it, they wouldn't be able to go near as fast, would they? Okay, so we're going to start off by talking about level curves. Okay, now that's a pretty important diagram right there. Okay, so the centripetal force is towards the center, and it's being supplied by friction. Friction, right? So on a level curve, it's friction only that's supplying the centripetal force. Okay. Now, if you were to look at the car sort of from the rear end kind of thing, you've got the weight force down, which would be mass times gravity, and of course, they've got a small n here. What they're referring to there is Stefan's favorite, the normal force. So for a level curve, the centripetal force will be supplied by the friction force between the tires and the roadway. Here's an example. What must be the coefficient of friction between the tires and the level roadway to allow a car to make a curve of radius r, 350 meters, at a speed of 80 kilometers an hour? Okay, so we're asking for the value of mu. So asking for the value of mu. Now, I just need to be reminded what's on the next page here. Oh, yeah. So I do have. Yeah. Yeah. So we're going to go to the next page here now. So this diagram here, okay, now it doesn't matter that the road is not a complete circle. They're just going to talk about the radius of curvature. So if it were a circle, it would have a radius of 350 meters, okay? You'll notice that they've converted the speed to meters per second. Thank you. Right? They've converted the speed to meters per second. It says we can calculate the necessary centripetal force. I think you guys already have this, don't you? I'm the one that has to actually do it here. So I'm going to write FC is equal to mv squared over r, and you can see in your handout there that it works out. Now we don't have the mass of the car, do we? No. What are we going to do? No, it's just a car. Could be any car. Could be a Cadillac. Could be a little smart car. So we're going to write 1.41 m because we don't know the mass of the car. So the centripetal force is simply 1.41 times the mass of the car. 1.41 times the mass of the car. Now, the normal force over here is equal to mg, and once again, we don't have the mass of the car, so we're going to write the normal force as 9.8 m. Right? So we're going to combine them together. For this flat curve, the centripetal force is supplied by the friction force, which is Ff. Ff is equal to mu Fn, or mu 9.8 m. My centripetal force is equal to my friction force, and so I make these two equal to each other. Mu 9.8 m is equal to 1.41 m, and guess what happens? The mass of the car cancels out, and you get a mu value of 0.141. So the coefficient of friction must be 0.141 or greater for the car to go around that curve. Does it matter how big the car is? No, it does not. Okay? Because, think about it. The bigger the mass of the car, the more it pushes down, which means it more pushes up, which means there's more friction, right? But because it's bigger, right, that means that you've got a bigger centripetal force. So it all works out.
So you have to have the uniform motion.
You're assuming that you're going around the curve at a uniform speed.
The coefficient of friction has to be
The coefficient of friction has to be 0.141 or bigger. Because if you get more, you'll have more friction, right? No? I guess there might be some point where you couldn't move. The friction would be so great that you couldn't actually move the car.
There wasn't enough friction, you would just keep going.
You would slide. You would like skid out of the.
That's what happens in this ice.
Yeah, exactly. There, you need to listen to me, not to Tyler. Tyler, stop talking to him.
So, can you just like do it without mass, like without casters trying to cast like just
Well, you could put if you knew the mass of the car, you could put it in, but you'd be multiplying by say 1,500 and then dividing by 15.
No, but I'll just do the question about mass pairs, like not show that like I cancel mass, just do the question.
Yeah, you can try.
With the mass?
No, no.
And just like ignore the M.
Oh yeah, I guess. I mean,
You don't have to.
I just sort of showed you how it would. Yeah. Okay. So of course, any coefficient of friction greater than 0.141 will keep the car from slipping. This is the minimum value for mu. Let's just highlight that, could we? This is the minimum value for mu. Now that's assuming the speed is 80. Now generally, yeah, because it said in the question that the speed was 80. Okay? Generally, when you go on the highway, there's not a sign that says, caution, frictional coefficient must be greater than 0.141. Generally, that's not the case, right? I've never seen something like that. Usually, they put up a sign that says, don't drive any faster than 80 or 90 or 70 or whatever, right?
How come you can't?
They built in a little bit of a
Huge.
buffer.
Like the ones
A little bit of a
like 40 kilometers an hour.
Those two like 90.
Yeah, and you're fine.
So if you're going faster, is there less friction then?
Maybe, no.
No, there's not enough friction to overcome the needed to produce the required centripetal force.
So the coefficient of friction.
No, the coefficient remains the same. The coefficient doesn't matter how fast you're going; it just matters how good your tires are. Right?
So the speed really doesn't have much.
No,
So this question just kind of
it does.
speed doesn't affect.
Like if you knew the maximum coefficient of friction is say 0.2, there is a certain speed that you can't go over. You'll just slide right out.
Well, I said that didn't affect
drift.
the coefficient of friction.
It doesn't affect the coefficient of friction. If you know the coefficient of friction, there is a maximum speed that friction will give enough force to produce the centripetal force. Right?
When you drift your car, is that why your nose always goes towards the middle? That's like they fight.
Maybe, yeah, I guess. Yeah.
When you drift, your front goes, but then your back end always wants to go
Yeah.
in. That's why you steer the opposite way.
I guess, yeah. Makes sense. Yeah. Okay, now, so notice that the force of friction is perpendicular to the velocity. It's still in the direction necessary to oppose the motion that would occur without friction. The car will slide away from the center to the right in this diagram if it encounters a patch of low friction surface like ice or oil. Therefore, the friction force is directed toward the center. Notice, too, that we are dealing with static friction, not rolling friction. The piece of the tire in contact with the road is momentarily at rest with respect to the road, certainly if you're going sort of sideways. The force of static friction is somewhat greater than the force provided by the kinetic friction if the tires start to skid. Okay, so here's what the engineer would have to figure out. What is the maximum speed that a 1,500 kilogram car can round a level curve if the radius of the curve is 100 meters and the frictional coefficient is 0.65? This is what the engineers would do when they have to determine, are we putting up a sign that says, slow down? So go ahead and try that.
You did.
Well, the first thing that I did was I went, I found the weight force.
What'd you get?
There's a variety of different ways. 1,500 times 9.8, right? And actually, you could just go, friction force is mu Fn, which is mu mg.
That's what I did.
That's what you did? Okay, so 0.65 times my 1500 times my 9.8. Does it have to be negative? No, because the friction, like the negativeness of the 9.8 is down, but does that matter with the friction force? No, it doesn't need to be negative. That doesn't. So it's 9,555 newtons. Now that 9,500 newtons of friction is what supplies the centripetal force, right? So Fc equals mv squared over r. So this value goes up here. The mass is 1,500. V squared, my radius was 100. Yeah, there's certainly lots of different ways. How many people got 25.2?
Yeah.
Awesome.
23. 8. 5, 8, 9, 3.
Now, did you notice that here, inside that 9555, I multiplied by 1,500, and what did I do over here? I divided, didn't I? Like I multiplied by 100, and then I divide by 1,500. So really, I could do what I sort of did in my example and just ignore the mass, right? I could put in here an m, and have like 0.65 times 9.8 times m, and then have an m right here, and then those m's would cancel out.
But you always ignore the math?
Whatever. Pardon me?
You always ignore the math?
Pretty much.
That's stupid. Why wouldn't you just make a formula so it doesn't involve math? Can you construct a new formula that doesn't have
Sure, we could.
Let's do it right now. Can we do that? It's fun.
Okay, well, give me the formula for the maximum V with no mass in it.
Maximum V.
Maximum V with no force in it. No mass in it.
V equals the square root of F.
It's real. Let's look at it this way, right? We know these two things are equal to each other, right? We know that FF is equal to FC. So this is mu mg is equal to mv squared over r. Cancel the masses. Solve for V.
Can we just do like mu
So that would be mu gr is equal to V squared. So V equals the square root of mu gr.
Okay, let's see if this works. So let's do squared. I was close.
You have square root.
I said V equals FC R squared.
Yeah. It should be fine.
Mass 1,500 times gravity.
No.
Well, I want you. The important part is I want you to understand this part, right?
Yeah. I got 1200.
Here's what I'll do. I'll only let you use it if you show me these three steps.
What?
Like, because I want you to. I don't just want it to become a let's plug in the number and here's the answer kind of thing. Because I might ask you I might also ask you, well, people want to drive 100. What radius of curvature should I use?
Oh. So this is just only by the maximum velocity.
This is only that's right. But this only works on level curves. Level curves. Level curves. Now, generally, we would multiply by 3.6 to get it in kilometers an hour. This works out to 90.9 kilometers an hour. So the highway engineers would likely encourage people to slow down. A radius of curve of 100 meters is actually pretty small. Like, what do you think the radius of curvature is on the track outside?
Probably 0.
Let's just.
Where does the radius go to? Like middle of the track?
Well, let's just draw the track here. No, it's not to the middle of the track. It would be like this is the track, right? So what we're talking about is that distance there, or anywhere around, right?
Right now?
100 is a full loop.
Well, Quinn, what's the
Or
what's the width of the football field?
the whole like the field or
Yeah, but the
Well,
football
I know.
field isn't the whole.
I know, but that gives us an estimate, though, right?
Let's just go measure.
Well, look at it this way. From there to there is 100. From there to there is 100, right? So that means that the curve should be roughly 100, right? So circumference of a circle is 2 pi r, right? So if we put that half and that half together, our circumference would be 200 is 2 pi r. So r would be 200 divided by 2 is 100, right? So it's 100 divided by pi.
I'd say it's about, if the field is 55 yards apart, and I'd say it's probably about 20 yards on each side.
So the radius is about 32 meters,
Now I can go measure it.
roughly.
It could probably be about 70.
Like if you walked from the inside lane to the other inside lane, it would be about 64 meters, roughly.
You have one of those campers?
I do actually.
It's
Okay.
one of those.
Now, could you drive a car around that curvature? Like
Yeah.
you could, but not at 90.
No.
There's no way. There's no way you drive that at night,
Drift it.
right?
Yeah,
But
yeah, yeah.
100 is pretty sharp too.
Okay.
All right, let's talk about bank curves.
Donkey Kong.
Okay, bank curves are important. So, civil engineers generally bank curves on roads in such a manner that a car going around the surface at the recommended speed does not have to rely on friction from its tires in the road surface in order around the curve. Okay? In other words, you can still do it in the wintertime. Suppose that the radius of curvature of a given curve is only 60 meters and that the recommended speed is 40 kilometers an hour. At what angle theta should the curve be banked? We're really coming up with a derivation here.
45.
Okay, so consider a car's mass m going around the curve. Do you think the mass is going to cancel out again?
Yep.
No.
Mass always counts.
Well, let me ask you this. If you're driving a semi, think about the curve there at St. Rose as you're making the corner on the highway.
That's a dangerous corner.
Fair enough. Does it matter whether you're driving a semi or a smart car, how fast you go around the corner?
Yeah.
If you're going to say the speed,
Like, do semis and smart cars travel at 100?
Yeah.
Of course they do. So it's starting to look like the mass cancel out, right? Okay. So consider a car of mass m going around the curve. The car's weight mg acts vertically downward. The road surface exerts an upward normal force F on the car. Actually, we're going to label it F. Can I label it F perpendicular?
No, that's stupid. That's great.
Let's label it F perpendicular. Okay? So here's the force. This is my Fn. I'll label it Fn. This is my Fn right here. Okay? This little triangle right here is the same as that triangle blown up. Okay? And this we're going to call F sine theta, and this we're going to call F cos theta. Now my mg, this one right here, is like this. Right? This is my, now do you remember that this angle here, which is this little guy angle in here, is the same as the angle of this one right here? Remember that?
Yeah.
Okay, so this is adjacent, so this is F cos theta. So what can you say about F cos theta and the weight force of the car, mg? They have to be equal, right? So F cos theta must equal mg. The horizontal component of the reaction force, F sine theta, that's this guy up here, acts towards the center of the curvature of the road. This is what provides, this component provides the force towards the center of the curvature, which the car experiences as it rounds the curve. In other words, F sine theta is equal to the centripetal force, which is equal to mv squared over r. Right? So in other words, we've got F sine theta right here, and I think you have to write this in. F sine theta is equal to mv squared over r. So what I've got is I've got F sine theta is mv squared over r, and I got F cos theta is equal to mg. How can I get them together so that my masses are going to cancel out? Well, now here's the one reason why you have to do all that identity proofs and pre-calc. Just so you know, everybody knows that
cos over
tan theta is equal to
sine over cos over sine over cos.
sine over cos. Do you know why?
Yes, because
Tan theta is the opposite over the adjacent, and so in other words, tan theta is equal to F sine theta all over F cos theta. Now, normally in math, you would just cancel the F's and it's sine over cos, right? But I don't want that because my F sine theta is equal to, in blue there, mb squared over r. And my F cos theta is equal to, in red, mg.
So that's the mass cancel right there.
Mass cancels out.
B squared D.
Tan theta is equal to v squared over r over g. So when it's like v squared divided by r divided by g. So can I not just write it like that?
Right. So should I be writing something?
Tan theta is equal to v squared over rg. That's the formula for bank curves.
Curves.
That's the formula for bank curves. Now, note that if the car attempts around the curve at the wrong speed, and this is the bank for the centripetal force to be provided by the normal force.
Why does that matter?
What it means is even if the road was completely ice covered, you could still drive around it because of gravity. Gravity would actually be, there would be enough component of gravity that would actually force you towards the center. Okay? If the road was frictionless, because what's providing this F sine theta? What's providing the centripetal force?
Gravity.
It's gravity, basically, right? Gravity is causing. Now, there's also because of the angle, there's that FD down the plane, right? That also helps out a little bit as well. That's not included here. So this is the FC to be provided by the normal force. In other words, if you want to drive faster than that, there has to be some friction. There has to be some friction, which there generally is. Okay? Note that if the car attempts to round the curve at the wrong speed, then the difference has to be made up by a sideways friction force exerted by the car's tires and the road surface. Unfortunately, this doesn't always work, especially if the road surface is wet. Okay, so now I think you've got, do you have an example there? Example number, I think you got to go back to example number 9, right? Yeah. You got to go back to example number 9, back a page. Try that one right there. This time I've switched it up a little bit. I'm asking for the radius. Well, we've already determined our formula for a banked curve. Tan theta is equal to what? V squared over RG.
How do you get the R of that?
Yeah, like the tan.
Well, how about we first take 120 and divide by 3.6. What is it? Oh, it's given. Oh, cool. Okay, 33.3. Okay, so we're going to write tan 25 is equal to 33.3 squared all over r times 9.8, right? So how do you get r out of there? Well, this is a divide by r. When the r goes up, oh, can't do that. When the r goes up there, over the other side, it becomes a multiply, right? So isn't it going to be r tan 25, or can I take the tan 25 and the r and just switch them?
That's what I did. Like,
Yeah. 33.3 squared divided by 9.8 tan 25. Now, what happens when you got two things on the bottom? You got to make sure you bracket them. You got to make sure you bracket them. You can.
They're like 240.
33.3 squared divided by bracket 9.8 times tan 25. 243. 243 meters. There you go. Okay, so that wasn't too bad. You've got now, in that package, there's some questions on bank curves and unbanked curves. I think there are also there might be a couple questions in the book talking about bank curves as well. I can't remember. I might have to look at it.
So,
All right. So remember, plan is test on Thursday. So you got the rest of the test is Thursday.
2 weeks notice.
I,
I told you yesterday.
yeah,
That's 3 days now.
which is what?
What is, hey, we've done like 2 things done.
Not a whole
I don't know,
lot.
I-
Should we go,
You know what?
Well, yeah, there's not before this, but I mean like.
Tomorrow I'll give you a breakdown of whatever what all there is.
Force, finding, like,
Basically, there's horizontal circles, vertical circles, bank curves, unbanked curves.
Oh, it is? What a stupid
Wait,
unit.
bank curves and
Unbanked curves. That was the first one we did.
That's all I got. Where's the other one? Yeah, upside down, look down there.